Hello students, in this video we'll discuss about the topic homogeneous function and Euler's theorem. So let us start with this topic. So firstly, to understand the problem, how can we solve the problems of the Euler's theorem? Firstly, we should know that what is the homogeneous function. So firstly, we are going to discuss about the homogeneous function and how can we recognize that either the given function is homogeneous function or not. Okay, so firstly, a function f of x y, say we are considering a function f of x y, means it is a function of x and y, is said to be homogeneous in x and y and is of degree n in x and y and is of degree n if it satisfies the following conditions. Any one of the following conditions, you can say that any one of the following conditions. So, what are the conditions? Number one, if f of xy is homogeneous in x and y, then f of xy, if I replace here x with some scalar lambda x and lambda y, then this is equal to lambda raised to the power n time f of xy, or second one is if we take the maximum power of the variable, say x outside, then we left with a function of y upon x, right? Y upon x means it is a function with variable degree 0, and because if I multiply with x power n, it means that the net degree of the function is n only. Or if we take the maximum power of the variable, say y as a common, then we left with a function of, say, x upon y, right? But if x upon y or y upon x, it simply represent that it is a function with variable having 0 degree, right? And if I multiply it with y raised to power n, it means that the net degree of this function is n only. Okay, for example, suppose that our function f of xy is, say, x cube plus x square y, right? So now, if you can see here the power of x is 3, here the power of x is 2, and power of y is 1. So the total power is 3, total power is 3. So we can say that this is a function whose degree is 3 and it is a homogeneous function. But let us try to check these conditions. So if I replace here x with lambda x and y with lambda y, then this is lambda x whole cube plus lambda y, sorry, lambda x whole square into lambda y. So this is lambda cube x cube. This is lambda square x square into lambda into y. So you can see here lambda cube is common throughout. So this is x cube plus x square y. So after taking the power of lambda outside, again we left with a function only. So it means that this function is homogeneous. So if it is possible to take this lambda outside, it means that your function is a homogeneous function. And what is the degree of this function? The degree of this function is equal to the power of lambda. Here the power of lambda is 3, so it means that f of xy is, it implies that f of xy is homogeneous and is of degree 3. F of xy is homogeneous and is of degree 3, right? Let us consider the same example in other way. So what is the maximum power here? Here the maximum power is 3. So if I take x cube common, so it can be taken as 1 plus x square y upon x cube. So you can see here 2 power of x get cancelled out. So this is x cube into 1 plus y upon x. So 1 plus y upon x means it is a function of y upon x, right? So it is of this type. It is a function of the form y upon x and the power of the variable is 3. So it means that it is a homogeneous function with degree 3. Another one is we can take the maximum power. The maximum power is 3. So I can take y cube also common. If I take y cube common, so we have x cube upon y cube upon x square y upon y cube. So here we can see one power of y get cancelled out. We get y cube. This is x upon y whole cube. And this is x upon y whole square. So basically this is a function of x upon y with variable x upon y only. So it is a function because here the power of x is 3, power of y is minus 3. Okay, so the net degree is 0, net degree is 0. So it is a function with degree 0. And if I multiply with y cube, it means that f of xy is homogeneous and is of degree 3 and is of degree 3. Okay, or some other example we can take here. Suppose I can take another example that f of xy is equal to x square plus y square upon x plus y. Now, in this case, it is a rational function where you can see here the power of the numerator is 2 because the power of x is 2, the power of y is 2, and in the denominator, power of x is 1, power of y is 1. So the degree power is 1, numerator power is 2, so the net degree is 2 minus 1, that is 1. Okay, how can we check this? So I can take maximum power common from the numerator. I can take the maximum power of x from the denominator. Okay, so now if you just look at this particular one, it is a function with variable y upon x. And here one power of x get cancelled out. So we left with x power 1 time function of y upon x. So this is a homogeneous function with a degree 1. Sorry. Sorry. Or other ways, what can we do? We can replace x with lambda x, y with lambda y. And this is lambda square x square, lambda square y square upon lambda time x plus lambda time y. So lambda square common from the numerator and lambda common from the denominator. So if I cancel out lambda here, so it is x square plus y square upon x plus y. Now you can see here again lambda can be taken outside and this is nothing but your function f of xy. So lambda power 1 time f of xy, it means that your function is homogeneous and the degree of the function is 1. But sometimes your function is not homogeneous. Okay, so for example, I consider f of x as sine inverse of x square plus y square upon root x plus root. So in this case, if you simply remove this particular part, then you can see here this function is homogeneous because degree of numerator is 2, power of x is 2, power of y is 2, power of the denominator x is 1 by 2, y is 1 by 2, so the net power is 1 by 2. So here the net degree is 2. So the overall degree is 2 minus 1 by 2, that is 3 by 2. But because of the presence of sine inverse, this function is not homogeneous. Okay, so it means that this function can be made homogeneous if I remove sine inverse from here. Otherwise, this function is not homogeneous. This function is not homogeneous, right? So this is how we can identify that either a given function is homogeneous or not. We can directly identify our function also. Otherwise, we can use any one of these properties of homogeneous function to check that either the given function is homogeneous or not. Okay. Now, based on this, we have one important theorem that is Euler's theorem. So let us firstly discuss about this theorem. So what this theorem states that if f of xy is a homogeneous function in x and y and is of degree n then it gives us two important results. One, that x time curly f upon curly x plus y time curly f upon curly y. This is equal to n time f. What does it mean? If your function is a homogeneous and we want to find out the value of this particular expression, then the value of this expression is simply equal to n time. What is n? N is the degree of the function. N time the function only. Okay, simply multiply the degree with the function. You can get the answer directly. And the second important result is x square time curly square f upon curly x square plus 2xy time curly square f upon curly x curly y plus y square time curly square f upon curly y square. This is equal to n into n minus 1 time f. Okay. Let us consider a small example to verify the same. Suppose that we are considering use a function xk plus ysk. So clearly it is a homogeneous and the degree of this function is 2. Okay. So to verify this particular result, I'm calculating the derivative of u with respect to x. So if I'm differentiating with respect to x, it means y is treated as constant. So derivative of x square is 2x. And similarly, if I differentiate u with respect to y, then its derivative is 2y. Okay. So now we are going to calculate this expression. So x curly u upon curly x plus y curly u upon curly y. So I multiplied with x, so it is 2x square. I multiplied with y, so it is 2y square. So 2 common x square plus y square. But what is our function? This is u, so it is 2 times u. What do we find out here? This is equal to 2 times u. This is the first result. For second result, I differentiate again. So what is the second order derivative? So curly square u upon curly x square. So first order derivative is 2x. So curly by curly x of 2x. So its value is 2. Curly square u upon curly y square. This is curly by curly y of 2y. It is also 2. And curly square u upon curly x curly y, which is same as curly by curly x of curly u upon curly y. Or I can differentiate curly by curly u upon curly x because the partial derivatives are continuous because it is a polynomial function. So in that case, the partial derivatives are continuous. So curly square u upon curly x curly y is same as curly square u upon curly y curly x. Okay. So its value comes out to be either I differentiate y with respect to x, it is 0, or I differentiate curly u by curly x with respect to y, its value is 0. Okay. So now if I calculate this part, x square time curly square u upon curly x square, 2xy time curly square u upon curly x curly y plus y square time curly square u upon curly y square. So this is x square time 2, this is 0, this is y square time 2. So its value is 2 times x square plus y square, right? So this is 2u. And if you substitute here, what is n? It is 2. What is n minus 1? 2 minus 1 time u. So its value is 2u. As verified. Okay. So basically, with the help of this theorem, we can come up with a very important conclusion that if your function is homogeneous in x and y, then there is no need to calculate its derivative. We can directly get the value of this particular expression. So this kind of expression plays a very important role, especially when we want to solve the MCQ type problems, right? So if we can identify that the given function is homogeneous, then with the help of Euler's theorem, we can directly get the value of this expression, right? Now, let us consider the proof of this theorem. It is not the difficult one, so we can easily prove this particular theorem. So because f is homogeneous, sorry, because f is homogeneous in x and y and is of degree n, and is of degree n. So it means that f of xy can be written as x raised to the power n times some function of y upon, right? So now we firstly calculate its derivative with respect to x. So we are going to apply here the product rule because both the function depend upon x. So product rule first function, derivative of second plus second function, derivative of first. So here we are going to apply the chain rule, the derivative composition of a function, that this function depend upon single variable, but this single variable depend upon two variables. Like that is the function of u, and u is the function of x and y. So what is the derivative of z with respect to x? This is f dash u into curly u upon curly x. So we are going to use this result here. So its derivative is g dash y upon x into derivative y upon x is minus y upon x square. Okay, because derivative of x power n is anytime x power n minus 1. Because if we differentiate with respect to x, then y is treated as constant. Plus g of y upon x as it is, and derivative of x power n is anytime x power n minus 1. So if we solve this particular part, so this is minus y x power n minus 2 times g dash y upon x plus n time x power n minus 1 times g of y upon x. This is the derivative of function with respect to x. Now, if we differentiate with respect to y, so curly f upon curly y. Now, when we differentiate with respect to y, then x is treated as constant. So it means that x power n is constant. So we can take it outside. We simply differentiate g of y upon x with respect to y. Again, we are using the derivative of a composition of the function. So derivative of g is g dash. Derivative of y upon x is 1 upon x. So its value comes out to be x raised to the power n minus 1 times g dash y upon x. Right? Now, both the first order derivatives are known to us. Now, we are trying to check the value of the first expression, x curly f upon curly x plus y curly f upon curly y. So, if we calculate this, x curly f upon curly x plus y curly f upon curly y. So, I'm going to multiply this entire expression with x. If I multiply it with x, so it is minus y x power n minus 1 times g dash y upon x plus this is n time x power n times g of y upon x plus I have multiplied this expression with x and the second expression with y, means this with y. This is x power n minus 1 y g dash y upon x, right? So I multiply the first expression with x, this expression with x, and this expression with y, and adding. So you can see here this and this term get cancelled out. So what do we left with? This is n time x power n times g of y upon x. And this is nothing but our function. So this is n time f. So what do we conclude from here? That x curly f upon curly x plus y curly f upon curly y is n time f. This is the required for the proof of the theorem. Okay. Now let us come to the second part. For second part, we are going to use this particular result. So for this one, what can we do? We differentiate this entire expression. Differentiate equation number 1 with respect to x, keeping y as a constant. Keeping y as a constant. What do we get? It is here we apply product rule because both are function of x. So first function derivative of second plus second function derivative of first, and here y is constant. curly square f upon curly x curly y. This is n time curly f upon curly x. Say this is equation number 2. Now again, differentiating equation number 1 with respect to y, at this time keeping x as a constant. This time keeping x as a constant. So we'll get, now when we differentiate with respect to y, x is constant. So x as it is curly square f upon curly y curly x. But here we need to apply product rule. First function, derivative of second, plus second function, derivative of first. This is n time curly f upon curly y. Say this is equation number 3. Now to prove of this particular expression, we need second order derivative with the x is with x square. Second order derivative with respect to y with y square. But here we have second order derivative with x only. So I'm going to multiply equation number 2 by x and 3 by y, 2 by x and 3 by y, and adding. So when we adding, this is x time xk time curly square f upon curly xk. Now firstly I'm considering this term xy time curly square f upon curly x curly y, and this if I multiply it with y, this is xy time curly square f upon curly y curly x, plus this term y square time curly square f upon curly y square, and rest of the term is first order 1 and 2. I multiplied with x, so it is x curly f upon curly x and y curly f upon curly y. And in the right hand side, n is again common, and I multiplied first with x and second with y. Now here xy, because I told you the first order partial derivatives are continuous, so it means that they are same. So this is x square time curly square f upon curly x square plus 2xy time curly square f upon curly x curly y plus y square time curly square f upon curly y. And I'm going to take this term on the right hand side. Okay, so what do we have? This is n. But what is the value of curly f upon curly x? This particular expression is nf. So this is n into nf minus. This term is also nf. So nf is common, n minus 1, or n into n minus 1 into f. So this is the proof of this theorem. Okay. So what do we conclude from here? That the first order derivative expression x curly f upon curly x plus y curly f upon curly y, this is equal to nf, and second order derivative expression is equal to n into n minus 1 into f. Now we are going to discuss some problem based on the Euler's theorem. Okay, let us consider some problem here. Okay, suppose we'll consider a problem. Firstly, question is, suppose that your function is u equal to log of square root of x square plus y square upon x. Then we need to find out the value of x curly u upon curly x plus y curly u upon curly y. Okay, so we want to find out the value of this particular expression. So let us see how do we calculate the value of this expression here. So what we are going to do, so if we just look at this particular expression, we know that according, if your function is homogeneous, then according to the Euler's theorem, this is equal to n time u, where n is the degree of the function. So firstly, I'll try to check that either the given function is homogeneous or not, right? So we are checking here u equal to log of. This is square root, and inside square root we have a quadratic polynomial x square plus y square. So it means the degree of this part is 2. And because of square root, we can simply take the half of this power. Half of x square plus y square means the degree is 1. And in the denominator, degree is also 1. Okay. So how do we check here? I can take x common. So we have 1 plus y upon x whole square upon x. Suppose that we are considering our variable x as greater than 0, right? So here power of x get cancelled out. So basically this is the homogeneous function. This is the homogeneous function degree 0, where the degree is 0, because this is of the form log of square root of 1 plus y upon x whole square. Okay, or what can I do? I simply take x inside the square root sign. Instead of taking outside, what can we do? We can take x inside the square root sign, then it becomes x square, and separating the term. This is 1 plus y upon x whole square. So there is no power of x, it means that x power 0. So it is a homogeneous function with degree 0. So what is n here? 0. Then according to the Euler's theorem, what do we have? X curly u upon curly x plus y curly u upon curly y. This is equal to n time u. And what is n? It is 0. So its value is 0. So this is the solution of this problem. Okay. So there is no need to find out the derivative of this function, because here we find that your function is homogeneous itself. So we can directly get the answer, right? Okay. Now, the another thing is, if this function is having degree other than 0, then this function is not homogeneous because of the presence of log. For example, suppose that your function is u equal to log of square root of x square plus y square upon x square. Okay, then what does it mean? This is log of square root of x square plus y square upon x power 4. Then this is not homogeneous function, right? Because in that case, if I take the maximum power common, so here I can take, say, x common from the numerator. So this is square root of x square plus y square upon x square is already outside, so one power get cancel out. So we have x square plus y square upon x square, but here we have x square plus y square square root upon x. So in this case, if I take it inside, then this is equal to log of, sorry, wait. If I take x outside, then we have 1 plus y upon x whole square. And here we have a x square. So one power get cancelled out. So we have a log of x power minus 1 into square root of 1 plus y upon x whole square. So because of the presence of logarithmic function, this function is not homogeneous. So how do we reduce it into homogeneous? So what can we do? We can take exponential on both sides. So I can write my function as e power u is equal to x power minus 1 times square root of 1 plus y upon x whole square. So it is like x power minus 1 times some function of y upon x. So we can say that e raised to power u is homogeneous in x and y and is of degree is equal to power of x, that is minus 1. Okay, so according to the Euler's theorem, what do we have? In that case, it is x times curly by curly x of e power u plus y times curly by curly y of e power u is equal to n times e power u, that is minus 1 times e power u. Okay, and what is the derivative of e power u? So it is again composition of the function, because u is a function of x and y. So here the derivative e power u is e power u into curly u upon curly x. This is y time e power u curly u upon curly y. This is minus of e power u. So e power u taken outside, x curly u upon curly x plus y curly u upon curly y. This is equal to minus e power u, cancel out. So its value comes out to be minus 1. Okay. So it means that sometimes the given function is not homogeneous, but we can convert that function into the homogeneous form. So if it is possible to convert it into that form, then we can apply Euler's theorem for the reduced function. Okay. Let us consider another example. Suppose the question is, suppose the question is the function u is equal to y cube minus x cube upon y square plus x square, and we need to find out the value of x curly u upon curly x plus y curly u upon curly y, and also x square time curly square u upon curly x square plus 2xy time curly square u upon curly y square plus y square time curly square u upon curly y square. So we need to find out the value of these two expressions. Okay. So what we are going to do? So in this case, again, if you just look at here, that this particular is equal to n time u, and this expression is equal to n into n minus u according to the Euler theorem, but the condition is if u is homogeneous. If u is homogeneous function. So now if we just look at here, the power of y is 3, the power of x is also 3. So the total degree of numerator is 3. The power of y is 2, the power of x is 2. So the total degree of denominator is 2. So numerator upon denominator means we are taking the difference. So the net power of this function is 1. How do we check this? We replace x with lambda x and lambda y. So this is lambda cube y cube plus lambda cube x cube upon lambda square y square plus lambda square x square. So lambda cube common from the numerator, y cube plus x cube upon lambda square common from the denominator, y square plus x square. So 2 power of lambda get cancelled out. So it is lambda time y cube plus x cube upon y square plus x square, which is nothing but equal to lambda raised to power 1 time u of xy. So because it is possible to take lambda completely outside, so hence we can say that u is a homogeneous in x and y, which implies that u is homogeneous in x and y and is of degree 1. So according to the Euler's theorem, the value of the first expression x curly u upon curly x plus y curly u upon curly y, this is equal to n time u. So what is n here? N is the degree of the function. So it is 1 time u. And what about the second expression? X square square u upon curly x square plus 2xy square u upon curly x curly y plus y square time square u upon curly y square. This is equal to n into n minus 1 into u. So here n is 1, 1 minus 1 into u. So 0. 0 into 1 is 0. So answer is 0. So in this case, its value comes out to be u, and in this case, its value comes out to be 0. So this is its value is u, and this value is 0. Okay, I hope it is clear to you. Okay, so whenever we want to calculate the value of the expression of this kind, where the order of the derivative with the power of the variable, independent variable, is same. Okay, first order for second order derivative, then we can use the Euler's theorem result. Okay, let us consider another problem here. Suppose the given function is u equal to tan inverse of x cube plus y cube upon x minus y, and this time we need the value of x square curly square u upon curly x square plus 2xy curly square u upon curly x curly y plus y square time curly square u upon curly y square. So now if you can see here, in this case your function, if I simply forget about this tan function, then this function is homogeneous, but it is of degree 2 because degree of numerator is 3, the degree of denominator is 1. But because of the presence of tan inverse, this function is not homogeneous. Okay, because if I replace x with lambda x and y with lambda y, then this is tan inverse of lambda cube x cube plus lambda cube y cube upon lambda x minus lambda y. So this is equal to tan inverse of lambda cube common x cube plus y cube and lambda common x minus y. So here the power of lambda is 2. But it is not possible to take lambda square outside this function. So it is not equal to lambda power n time, cannot be expressed in the form of lambda raised to power n time u of x. It means it is not homogeneous, right? But if I simply remove this tan function, or I can apply tan on both sides. So I can write, say, the first function as tan u is equal to x cube plus y cube upon x minus y. Now this function is homogeneous. This function is homogeneous in x and y and is of degree n equal to 2. So you can see here, if I forgot about this function, then this particular part is homogeneous in x and y and the power of lambda is 2. So it means it is a homogeneous. So, but we need the value of second part. Okay, so what can we do? So we can say that according to the Euler's theorem, x curly by curly x of tan u. So here we are using the first order derivative result, although we need the second order. But why we are doing this? Because in that case, we can use this result for tan u, but not for u, right? But if I directly put here tan u, then it becomes a very complicated expression, right? So we are going to use the same concept what we have done in the derivation for the second order derivative, right? So this is equal to n time tan u. N time tan u means 2 time tan u. So here we apply the derivative composition. Derivative of tan is secant square times curly u upon curly x, y into secant square u times curly u upon curly y. This is equal to 2 times tan u. And if we divide throughout by secant square u, this is equal to 2 tan u upon secant square u. So this is 2 times sin u upon cos u. And secant square u means cos square u. So one power get cancel out. So 2 sin u cos u is sin 2u. So this is the value of the expression of first order. But we need the expression of second order. So we are going to use this as an identity. If this is equal to sin 2u. Okay. So what can we do? We differentiate this expression with respect to x. Like the same step we are going to follow which we have done for the derivation part. So here we get derivative of sin 2u. Derivative of sin 2u with respect to x. So this is equal to cos 2u into 2 times curly u upon curly x. And if I differentiate one with respect to y, so this is equation number 2, keeping x as a constant. So we'll get this is x times curly square u upon curly y curly x plus y curly square u upon curly y square plus curly u upon curly y into 1. This is curly by curly y of sine 2u. This is equal to cos 2u into 2 times curly u upon curly y. This is number 3. So what can we do? Multiply 2 by x, 3 by y and adding. So we can get x square curly square u upon curly x square first term. Now combine these two terms because we know that the partial derivatives are continuous. So this is y. One term and one term. I multiplied with x, I multiplied with y, so it is 2 times xy curly square u upon curly x curly y. And another term we need to consider here is this one, second order derivative with respect to y. So this is y square times curly square u upon curly y square. So rest all the term I'm keeping in the right hand side. So what term is there? Multiplied with x, multiplied with y. And this term here, it is 2 cos 2u is common. So this is x curly u upon curly x plus y curly u upon curly y in the right hand side. And here in the left hand side, we have x curly u upon curly x plus y curly u upon curly y. This is in the right hand side. So I'm going to keep this term in the in the right hand side only. So we can get the value of this expression as this is equal to 2 cos 2u into the value of this one is sine 2u. And when we take this term on the right hand side, this become minus sine 2u. So sine 2u is common. So we have a 2 cos 2u minus 1. So this is the value of the expression x square curly square u upon curly x square plus 2xy curly square u upon curly x curly y plus y square times curly square u upon curly y square. So this is the required expression in this case. Okay. So we have discussed the different kind of problem that could be asked on the basis of the Euler's theorem. So sometime the given function is directly homogeneous. In that case, we can apply the Euler theorem directly. But if your function is not homogeneous, but it can be reduced into homogeneous form, then firstly we reduce it into homogeneous form and then apply Euler's theorem to get the value of that expression directly. But if the expression is asked for the second order derivative, then if the function is directly homogeneous like the previous problem, then we can get this value directly n into n minus 1 into u. But if we have reduced our function into homogeneous form, then we'll not apply the identity directly for second order. What can we do? Firstly, we apply the identity for first order derivative, and then we use the same step which we have done in case of the proof of the Euler's theorem. That's the reason we have discussed the proof of the Euler's theorem so that you can understand that what and why we have followed this kind of step for the derivative of for the expression of second order derivative, right? I hope you will understand or grab the concept for the problems of Euler's theorem. But if you still find out any doubt or any query, you can ask your query in the comment box. I'll try to provide you the solution of the same problems. Thank you and have a nice day.